Okay, so we're on example 4. I just gave everybody a handout of this slide, which is the previous slide, so you can see that on the YOLO site, and just talking about regression equations and R values. So I will let you look at that. We're working on number 4, where we choose a regression equation. Everybody is taking a few minutes and putting these in list 1 and list 2, and then making a scatter plot of that. And so did everybody, if you are just going to start that right now, you can pause this and then do that and then come back. And so does everybody have a scatter plot where you can see those values yet? No? Okay. And I'll pause this a moment. Okay, so now you should have these in list 1 and list 2 and made a scatter plot. A question came up if you have an equation in there already. That was maybe a previous equation, so you can clear that out of the y equals. And your scatter plot might look something like this. And the scale that the book authors give, I disagree with for this particular problem. As you look at this, it appears as though the data could best be modeled by which one. Look at that handout and just kind of see for yourself, what model do you think might match this the best? And the models are given, with the drawn in curve or whatever. Anybody have a thought on that? It looks like it might be the exponential one. But what we're going to do is we're going to take a few minutes and we're just going to calculate lots of regression equations. So you have that data in your calculator, and you're going to find all these regression equations. Hopefully they're going to match mine. First, if you've cleared out your calculator, you want to turn the diagnostic back on. But let's just calculate the first one and see what happens. We're going to do a bunch of them, write a bunch of R values, and kind of see which one we want to pick. So I want you to do linear regression number 4. So just go to the calculator, and where is that? Calculate over to whatever. I can't think of what it says. And you're choosing number 4. And is 4 linear regression? Somebody tell me. Okay, so 4 is linear regression. And I want to know, when you do that, what the R value is. Okay, Logan, tell me 6 decimal places. Okay, and because sometimes these can be pretty close to each other, we want to see what they are. So number 5 is did you get that? Yeah. And so actually, Amy, just start with this next one. The next one you're going to do is number 5, quadratic. And on this one, it's going to give you R squared. Yes, but your diagnostic isn't on. Okay. Second. So now R squared is on there. What is it? And is there more? Okay, so I'm writing the whole thing. Now, I'm going to tell you something about your calculator, and I'm going to have to look at a calculator because I'm not going to do it on that calculator, but you can make the calculator find this value. When you look on the calculator screen, is that R like a capital R squared? Okay, I will change mine. On the calculator, it says capital R squared. And do you remember when we've done things like vars and y-vars? On your calculator, type the square root key. And I don't know, either old software gives you a parentheses or it doesn't. And then you're going to find R squared, the variable in here. And it's under vars. And then Y var, nope, just kidding. It's under vars and statistics, number 5. That's why I have to look at it. And then it's at EQ, which is equation. Do you see number 1 is regression equation? Arrow way down, it's like the very last thing, and it's a capital R squared. It's number 9. And so you have square root, and then when you type that, it should say R squared, close the parentheses, enter, and then you'll get what R is. Did that work for everybody? Give me a head nod for that if it worked for you. And then Casey, since I just asked you that, what is, so then that's R. Go ahead. That's good now. Yeah, I'll just go that far. I do write them really long because if I am gonna do that by hand, if I forget where to look or whatever. So do you agree quadratic is better than linear, right? So that's kind of that one. We're gonna do number 6, which is cubic. And that's gonna give R squared again. So I want to hear R squared. And I didn't look at that one. Is it a lowercase R squared or a capital? Okay, I thought it probably was again, but I didn't look at it, so I wasn't sure. So who can tell me what R squared is? Okay, wait, point, I'm ready. Okay, and then do that again where you're doing the square root, and then, okay, I'm trying to say it without looking at the calculator as much. Square root, and then vars, and then down to statistics. I do have to look every time. And then EQ, and then find that capital R squared, number 9. And who can tell me what they got for that one? Go ahead. Okay, so that one is even better, correct? I mean, so we're kind of seeing what they are. And personally, I wouldn't write down what the regression equation is. I would just find the R values and then pick the one I want and then redo that one and then say that's what I'm going to use. So then we're going to do number, 9 is next. We're going to do the LN regression. And I think that one will give you just an R value. Alex, whenever you have that R value, you can tell me what it is. Is yours doing the R, correct? Okay. Okay, and so it's not the one we want to choose, but we're really doing this exercise just to compare those R values and see what happens. Now try 0, the EXP regression. And am I right in thinking that's what we think is going to be good, right? And Madison, what is that? That R is 1. So actually, is that as good as it gets? Right? But I will just have you, just to practice, do the PWR, the power regression. And who has what that would be? I'm going to stop there because I ran out of room. But yes, so, finding a bunch of these kind of gives us what's happening. Now, the logistic regression does not give us that R value. So that you just kind of have to model it and kind of see which one it is. We know now that the exponential regression is our absolute best R value. So now calculate the exponential regression again, because that's what we're going to use. And we're going to say this is our exponential regression equation. And I have one written here. I'm not sure if it exactly gives me that. But what is that first number that goes right here? 999. So point what? 1 9. So, okay. So can I call that 1,000? Okay, I'm going to call that 1,000 times something raised to the t. And I'm going to just go 2 decimal places. Haley, do you have something that you could tell me what 1.78 raised to the t? And I could dump that in y1, and of course that would give me a little bit of a different value as I look at it. So that's my regression equation. I'm going to go back a couple slides and I'll come back to this one because I just need to know what's happening here. So it said use the data to determine a regression equation that best relates the profit of a website with the time it has been in business. So we've done that part, and actually maybe I will just write that here. That's, oops, P of t equals 1,000 times 1.78 raised to the t. And then it says determine the approximate time it will take for the website to earn a profit of $100,000 in 1 year. And so that is going to be when this is 100,000. We're going to do that on the calculator. So type this in Y1. 1,000 times 1.78 raised to the t. And in Y2, right now you're going to put 100,000. And that should be, oops, that should be a horizontal line across. And find that point of intersection. So when you're graphing all that, notice these things. Does this curve fit the points pretty well? It should look like it goes right through them because it's an R of 1. And then can you see that point of intersection? And have you found the point of intersection on the calculator, or make the calculator find the point of intersection? Do you remember how to do that? So to do that, you've got your graphs, right? And can you see the point of intersection? If you can't see the point of intersection, make your x max higher. You know, if it's 10 or 12 for x max, that should be fine. And you should be able to see your graph as well. And it's not going to go above the 31,000 because we want, oh yes it is, 100,000. So y max maybe should be past 100,000. And then can you see where they're intersecting? Can everybody see that they're intersecting, yes or no? Well, I'm just, you know, we're just going to look at it. Good. Okay, just to get that visual. And then make the calculator calculate the point of intersection. So second trace, which is calculate, and then intersection number 5. And then first curve, enter, enter, enter probably, and then it'll give you that point of intersection. What does x equal in that point of intersection? 7.9. Will it round to 8 or 9? 7.99. And that's how many years that will take. So I wanted to just go through and have you find a bunch of regression equations just to kind of see how that works. Now, the next thing we're going to do, and I wish we had a little bit more time today, but that's okay. And I think we'll be able to finish this tomorrow as we go. But the next thing we have to do is something called linearize the data. And so we're going to take data that does not look linear. We are going to linearize it so that we are going to make it look linear. And then we're going to find the linear regression. And then we're going to convert it back to whatever kind of regression we thought it might have been. So I'm just, that number 4, I had a lot of things for. So this is this next little part here, and it's called linearizing the data. Okay, I just wanted to make sure I'm still recording. I guess I am. The correlation coefficient is a measure calculated from a linear regression. So think about that. Correlation coefficient is calculated from a linear regression. Then how do calculators make a correlation coefficient if it's nonlinear regression? And so we're going to kind of delve into that. So we're going to kind of look now into the workings of a calculator so that we can be smart enough to kind of know how that is. The calculators linearize the data, and that is transforming the data so that it appears to cluster about a line, or it's linear looking. And so the process of transforming nonlinear data so that it appears to be linear is called linearization. Linearization. To linearize the data, a function is applied to either the x or the y or both, and then it's kind of graphed. This picture I want you just to look at. We're not going to do this problem as we go through, but here's our original data. And actually I will circle things so that the people who are not here can see. Our original data is these numbers, so we would put these in list 1 and list 2. And this is the graph of the equation. So, you know, it's kind of typical, kind of like that last one that we looked at. To linearize the data, look at what they're saying these are. This would be, is still list 1 because it's identical to the list 1 that was over there. But this would be not, we've used list 1 and list 2. So this would be list 3, and we would define list 3 as the ln of list 2. List 2. And we'll do that in a minute with a different example. But we find the natural logarithm of that data, and that will give us, and it'll just dump all that in. You do not have to do that one character at a time. It will do that for the whole thing. Then when you graph it anew, and notice that this is x, but this is the ln of y, it looks very linear. Do you agree that that looks like a line would match there? And then we're going to find the linear regression equation, and we're going to learn something new, and that is calling our changed y value into y hat. And we're going to call it y hat because it's a y value, but it's a y of kind of a transformation that we've used there. And so we'll be kind of looking at that as we go. So now the book authors are giving us a guide for transformations for linear data. So to linearize data modeled by, so if our data looks like it's a quadratic function, we graph instead x the square root of y. So take a minute, you're going to want to write these down. An exponential function, and we know what kind of that would look like. Then we transform our values into x and the ln of y. If it's logarithmic looking, then we use the ln of x and just plain y. And if it's a power function, y equals ax to the b, we use the log of x and the log of y. I have this, and this is the best I could do typing. I'm using the caret key, but it is just a little like, it's called a hat. And so X hat is red X hat, and Y hat are the predicted values from a regression line. So if we've changed something, then it has to have that hat on it. If we don't change it, it just stays as a regular X. So like if you look at this power function, this would be X hat and Y hat. But if you look at the logarithmic one, that would be X hat and just plain Y. Do you agree? Because if we just change whatever one we manipulate or change, then that's the one that is going to get the hat, and the other one can just stay. Yes, yep, so I'll write these. This would be X and Y hat, and this would be X and Y hat. And so the hat part is kind of generic, it could be logarithm, it could be the square root of something, there could be actually some other transformation, but here that's what we'll be looking at. All right, are you ready to try one yet? Oh. Okay, so we're going to linearize the data. First, I'm going to read this. It says, make a scatter plot of the data and linearize the data, assuming a power model. So will you write, as you're starting number 5, you probably want to write this table in your notes. And actually, to be honest, I'm going to tell you that you're going to leave maybe some space for some other tables. You might want to write those in your notes as you go through this, and just write yourself a note that it's going to be a power model. And so it says graph, make a scatter plot, then linearize it, graph the linearized data and find the linear regression, then use the linear regression to find a model of the original data. So this is a kind of big exercise for us in kind of manipulating things. So I would write that down, and then I would type this in list 1 and list 2 and make the scatter plot. Scatter plot. And I'll give you a moment to do that. Right? Yes. Okay, so when you graph that, the scatter plot should look like this, and it's also on the next slide if you want to see it a little bit bigger. And now we've been told that this is a power model, and so we know that when we linearize the data for a power model, we're using the ln of x and the ln of y. And so these next 2 tables on our list, so you're going to go to list 3, and you're going to name that as the ln of list 1. Do you know how to do that? Give me a head nod right now so I know if I should say that out loud. Do you know how to do that? So you go to the top of list 3, so it says list 3 equals, and way down at the bottom of the screen it'll say list 3 equals, and you're going to just type the ln key and then second one for list 1, and then enter, and it should just dump those right in there. And I'll write what they are. You should not have to, calculate the ln for everyone. And then list 4 is going to be the ln of list 2. And I'll write those in there just so that you can kind of see them and kind of feel confident about what you have there. Okay, give me a comparison to my table and your table. Give me a head nod if you have that or something very close to that. Yes, I'm seeing at least a few head nods. So that is our data, and this is X hat and Y hat because we changed both lists. If we only change one list, then only one of our things has a hat on it as we go. So we have made the scatter plot, and now I want you to graph this linearized data. So now you're going to make a scatter plot, and when you do this scatter plot, you're going to use which lists? List 3 and list 4. So for this scatter plot, you have to go to second, y equals, and that's the and go to the scatter plot and just keep using that plot 1, but you have to have it say list 3 and list 4 as the lists. And so go second y equals, and then to scatter plot or whatever it says. So second y equals, so to that first plot, and it should already be on, go down to the X list and go second 3 and go to the Y list and second 4. And then actually I'm going to have you have the calculator make the window, and I think you can do that. Will somebody tell me if this works? That when you do that, you're going to go zoom fit. Where is that? Zoom 0. Zoom fit. And so then Zoom Fit is meant for scatter plots, and so it should give you something that's pretty good there. And the point should look linear now. Does it look like dots that are in a line? Let me see it, flash it towards me. Is it dots? Are yours dots? It should be dots if you did that. I'll go to this slide and I will show you the linearized data. And let me get rid of that. And here's what that scatter plot should look like. Does it? Okay, so like, look at my scale. Maybe change your scale to be my scale. My scale goes from 0 to 2 by 0.1 and from -2 to 6 by 0.5. So see if you can change that to that and have that. Do you agree that that's called linearizing the data? Do you agree that the data now looks linear, right? But it's the same data, but it's been transformed. So I'm going to cut that. And I'll put it back on this first one. So did you get all that? Paste. Okay. Now, the next thing you're going to do, and this is where I'm going to leave you, and I'll pick up with this tomorrow. You're going to find the linear regression of list 3 and list 4. So, and I'll just write that as a direction now. Find linear regression of list 3 and list 4, and then we'll work on that tomorrow.